Here begins the essay. The year 1965 witnessed the publication of a seminal paper, Conservation of Orbital Symmetry, authored by Robert Burns Woodward and Roald Hoffmann. This work, antecedent to their more expansive 1969 monograph and the subsequent Nobel Prize awarded to Hoffmann alone, revolutionized the understanding and prediction of pericyclic reactions. This essay undertakes a comprehensive, section-by-section, critical evaluation of the claims and arguments presented within that foundational 1965 document. The focus remains steadfastly on an analysis of the internal logic, evidence, and methodology employed, thereby revealing a nuanced understanding of its enduring impact and subsequent Section 1 Introduction to Pericyclic Reactions and Woodward-Hoffmann Rules. The introductory portion of the 1965 paper delineates pericyclic reactions as a class of concerted reactions possessing cyclic transition states. It establishes the core premise that the stereochemical outcome of these reactions is governed not solely by thermodynamic considerations, but primarily by the symmetry properties of the molecular orbitals involved. This represents a departure from prior, often intuitive, explanations based on steric hindrance or simple energetic arguments. The authors explicitly state that reactions proceed along pathways where orbital symmetry is conserved. The paper proposes a set of selection rules dictating whether a particular pericyclic reaction will proceed in a thermally allowed or photochemically allowed manner, dictated by the symmetry of the highest occupied molecular orbital, abbreviated HOMO, of the reacting system. This section's claim hinges on the assumption that the system's evolution from reactants to products occurs along a pathway that minimizes changes in the electronic structure. The initial assertion, while revolutionary, lacks immediate quantitative rigor. The elegance of the proposal, at this stage, primarily resides in its predictive power and explanatory capacity vis-a-vis existing experimental observations. The claim of orbital symmetry conservation implicitly assumes an adiabatic process, where the system remains on the same electronic potential energy surface throughout the reaction. Section 2 Electrocyclic Reactions and the Frontier Molecular Orbital Approach. Electrocyclic reactions, a subclass of pericyclic reactions, see the formation of a sigma bond between the termini of a conjugated pi system, or the reverse process. The paper classifies these reactions as either conrotatory, wherein the substituents rotate in the same direction during ring closure or opening, or disrotatory, where the substituents rotate in opposite directions. Woodward and Hoffmann pinpoint the symmetry of the highest occupied molecular orbital as the critical determinant for a thermal electrocyclic reaction involving a 4n pi electron system, but a butadiene derivative. The highest occupied molecular orbital possesses the appropriate symmetry for a conrotatory process. Conversely, for a thermal electrocyclic reaction involving a 4n plus 2 pi electron system, like a hexatriene derivative, the highest occupied molecular orbital symmetry favors a disrotatory process. The paper demonstrates this by visually representing the pi orbitals and illustrating how their phases must align to allow for constructive bonding interaction during the formation of the sigma bond. This section explicitly argues that the observed stereospecificity stems directly from the symmetries of the interacting orbitals. The approach, relying on frontier molecular orbital theory, a simplification of all possible molecular orbital interactions, is justified by the claim that the frontier orbitals, namely the highest occupied molecular orbital and the lowest unoccupied molecular orbital, exert the dominant influence on reactivity. The argument's elegance lies in its ability to predict the stereochemical outcome based on a simple symmetry analysis, avoiding complex calculations or detailed mechanistic considerations. The paper does, however, acknowledge that steric factors can sometimes override the symmetry rules, particularly in cases where bulky substituents hinder the preferred mode of rotation. Section 3 Cycloaddition reactions and the role of suprafacial and anterafacial interactions. Cycloaddition reactions characterized by the joining of two pi systems to form a cyclic duct, are dissected through the lens of suprafacial and anterafacial interactions. Suprafacial denotes bonding occurring on the same face of a pi system, whereas anterafacial signifies bonding occurring on opposite faces. The paper asserts that the selection, rules for cycloaddition, reactions depend on the total number of pi electrons involved in the reaction, with thermal reactions favoring suprafacial-suprafacial interactions for 4n plus 2 pi electron systems and suprafacial-anterafacial interactions for 4n pi electron systems. The authors demonstrate this with the archetypal Diels-Alder reaction, a 4 plus 2 cycloaddition, proceeding in a suprafacial-suprafacial manner due to the favourable symmetry match between the highest occupied molecular orbital of the diene and the lowest unoccupied molecular orbital of the dienophile. The paper tackles the, at the time, less common anterafacial cycloadditions as theoretically possible but sterically challenging. The claim that suprafacial anterafacial cycloadditions are allowed but often unobserved hinges on the geometric constraints imposed by the cyclic transition state. The analysis provides a powerful framework for understanding the stereospecificity and regioselectivity of cycloaddition reactions. The restriction, the suprafacial interactions, particularly for smaller ring systems, reveals an important consideration of the actual physical constraints of the reaction pathway, while orbital symmetry permits anterafacial addition. Its realization is often hindered by geometric strain within the transition state, a subtle but crucial qualification. Section 4. Sigmatropic reactions and hydrogen shifts. Sigmatropic rearrangements, migrations of a sigma bond within a molecule, are analysed meticulously. The paper categorizes these reactions based on the number of atoms over which the sigma bond migrates. These are denoted by the notation I, J, where I and J represent the number of atoms in each fragment involved in the migration. The rules are similar to those for cycloadditions, with selection rules dictated by the number of electrons involved. For example, a thermal 5-sigmatropic hydrogen shift is predicted to proceed suprafacially, while a thermal 3-sigmatropic hydrogen shift is predicted to proceed anterafacially. The argument relies on the symmetry of the orbitals involved in the bond-breaking and bond-forming processes. The authors emphasize that the anterafacial pathway, while symmetry allowed for 1-3 shifts, suffers from significant steric hindrance due to the geometric requirements of the transition state. The assertion that suprafacial 5 hydrogen shifts are more common aligns with experimental observations, further validating their theory. The critical aspect highlighted is the balance between orbital symmetry constraints and steric accessibility. The theoretical possibility of anterafacial migrations exists, but practical limitations often favor suprafacial pathways even when the latter seemingly violate symmetry rules on a superficial level. The subtle interplay between theory and reality becomes evident. Section 5. Group transfer reactions. Group transfer reactions, involving the transfer of a group from one molecule to another, are considered a category of concerted reactions amenable to orbital symmetry analysis. The paper classifies these based on the number of electrons participating in the interaction. These are treated analogously to the other pericyclic reactions. The analysis suggests that reactions proceeding with retention or inversion of configuration at the migrating center are controlled by the symmetry properties of the orbitals interacting during the process. The paper posits that retention and inversion pathways depend upon the number of participating electrons. The conclusions regarding group transfer reactions extend the applicability of the orbital symmetry principles to a broader range of reactions. The analysis of group transfer reactions provides a unifying framework incorporating a broader scope of chemical transformations under the umbrella of conservation of orbital symmetry. This inclusion bolsters the theory's universality, showcasing its competence to interpret and predict outcomes across different reaction classes. Section 6. Photochemical reactions and excited state considerations. The analysis shifts to photochemical reactions, where molecules absorb light and undergo reactions from electronically excited states. The paper states that the selection rules for photochemical reactions are the reverse of those for thermal reactions. This change arises from the altered symmetry of the highest occupied molecular orbital in the excited state. For example, in a thermal electrocyclic reaction, a 4n pi electron system undergoes commutation, whereas in a photochemical electrocyclic reaction, a 4n pi electron system undergoes dissociation. The argument revolves around the occupation of formerly unoccupied molecular orbitals upon light absorption, thus shifting the frontier orbital configuration and thereby altering the symmetry requirements for the reaction to proceed. The paper emphasizes that the photochemical pathway provides access to reaction products inaccessible through thermal pathways. The reversal of selection rules under photochemical conditions unlocks new synthetic possibilities. The exploitation of excited state reactivity demonstrates the synthetic power of orbital symmetry considerations. This section brings a dynamic element, illuminating how light-driven processes can circumvent thermal constraints, generating novel compounds through previously inaccessible. Section 7 Generalized selection rules and the correlation diagram approach. The paper presents a generalized set of selection rules applicable to all types of pericyclic reactions. It also introduces correlation diagrams depicting the relationship between the molecular orbitals of the reactants and the products. The authors claim that reactions proceed along pathways where the symmetry of the molecular orbitals is conserved during the transformation. Correlation diagrams provide a visual tool for determining whether a particular reaction is symmetry-allowed or symmetry-forbidden. A symmetry-allowed reaction is one in which all bonding molecular orbitals of the reactants correlate with bonding molecular orbitals of the products, and conversely, all antibonding molecular orbitals correlate with antibonding molecular orbitals. Symmetry-forbidden reactions involve crossings of bonding and antibonding orbitals, leading to high-energy barriers. The correlation diagram approach offers a more rigorous method for assessing orbital symmetry conservation, moving beyond the frontier orbital approximation. The construction of these diagrams provides a visual means confirming the energetic feasibility of a reaction along a particular pathway. Their incorporation lends a degree of quantitative sophistication, permitting validation of predictions independent of frontier orbital considerations. Section 8 Deviations from the rules and steric effects. The paper acknowledges deviations from the predicted outcomes based on orbital symmetry rules. Steric effects, such as bulky substituents hindering specific reaction pathways, are cited as one cause. The authors admit that solvent, effects and other environmental factors may also influence reaction rates and stereoselectivity. The argument concedes practical limitations to the absolute predictive power of the theory. Recognition of exceptions strengthens the theory by establishing boundaries for its applicability. It demonstrates a sophisticated awareness of the intricacies of chemical reactions, acknowledging that orbital symmetry is a significant but not sole determinant. This transparency enhances the credibility of the proposed principles. Section 9 Limitations and Future Directions. The paper concludes by discussing the limitations of the presented theory and suggesting directions for future research. The authors suggest that more sophisticated computational methods are needed to account for electron correlation and other factors not explicitly considered in their simplified model. It also suggests that further experimental studies are needed to explore the range of applicability of the orbital symmetry rules. The acknowledgement of limitations promotes intellectual humility. The implicit promise of future refinements encourages ongoing research. The identified avenues for further research demonstrate a forward-looking perspective, recognizing the dynamic nature of scientific inquiry. Section 10 Contemporary Reception and Subsequent Elaborations. Initial reception of the 1965 paper was met with both enthusiasm and skepticism. The elegance and predictive power of the Woodward-Hoffmann rules quickly garnered attention, but some chemists questioned the reliance on simplified models and the lack of rigorous quantum mechanical calculations. Subsequent theoretical work, particularly the development of extended Hückel theory and more advanced computational methods, provided further support for the orbital symmetry principles. Woodward and Hoffmann themselves expanded upon their initial ideas in their 1969 monograph, The Conservation of Orbital Symmetry, providing a more detailed and comprehensive treatment of the subject. The original paper served as a cornerstone, but the subsequent development of computational chemistry furnished more robust substantiation. The initial skepticism gradually ceded to widespread acceptance as theoretical underpinnings solidified. Subsequent elaborations demonstrated a commitment to refining and extending the original principles. Section 11 critiques and refinements of the Woodward-Hoffmann rules. While the Woodward-Hoffmann rules revolutionized organic chemistry, they were not without criticism. Some researchers argued that the frontier molecular orbital approach was overly simplistic and that other factors, such as charge transfer and solvation effects, could also play a significant role in determining the outcome of pericyclic reactions. In response to these critiques, more sophisticated theoretical models were developed to account for these additional factors. Furthermore, experimental studies were undertaken to probe the limits of the Woodward-Hoffmann rules and to identify specific cases where they might fail. The original rules served as an excellent starting point, but the process of scientific inquiry naturally led to refinements and modifications. The acknowledgement of limitations spurred further research, resulting in more comprehensive and accurate models. The ongoing debate concerning the relative importance of different factors in pericyclic reactions illustrates the dynamic nature of scientific progress. Section 12 Impact and Enduring Significance. Despite critiques and refinements, the 1965 paper on the conservation of orbital symmetry has had a profound and lasting impact on the field of organic chemistry. The Woodward-Hoffmann rules remain a valuable tool for predicting the outcome of pericyclic reactions, and they have been widely incorporated into organic chemistry textbooks and curricula. The paper also stimulated a vast amount of research on the theoretical underpinnings of chemical reactivity, leading to the development of new computational methods and a deeper understanding of the factors that govern chemical reactions. The practical implications of the Woodward-Hoffmann rules are significant, with applications in the design of new synthetic strategies and the development of new materials. Their predictive power has greatly accelerated progress in diverse areas of chemical research. The enduring legacy represents a testament to the profound impact of a groundbreaking scientific contribution. In conclusion, the 1965 paper Conservation of Orbital Symmetry represented a truly transformative contribution. Its central claim, that the stereochemical outcome of pericyclic reactions is governed by orbital symmetry conservation, was supported by an ingenious analysis of various reaction types, including electrocyclic reactions, cycloadditions, sigmatropic rearrangements, and group transfer reactions. While simplifications were made, as with the reliance on frontier molecular orbital theory and an initial neglect of more nuanced steric or solvent effects, the paper's predictive power was undeniable. The paper's impact resonates even today, its principles enshrined in textbooks and informing synthetic strategies around the globe. The work's brilliance lies not only in its predictive capacity, but also in its ability to promote a deeper understanding of the fundamental principles governing chemical reactivity. The subsequent Nobel Prize, though awarded solely to Hoffmann, stands as a testament to the revolutionary perspective and scientific insight provided by this pivotal work, forever altering the course of organic chemistry.